So, it's on. Okay. So, this paper I'll be presenting today is Neural Appearance Model for Cloth Rendering. This paper was also co-authored by my undergraduate supervisor, Zara. So, yeah, I'll just get into it. Okay. So, why is rendering realistic cloth important? So, there's a bunch of users, especially in games, where characters wear different types of clothing, and as well as movies and TV shows, where there's lots of special effects involved, and being able to render them under realistic lighting or as well as the lighting in the desired environment. Secondly, there's also users in fashion and clothing industry, where designing a prototype or rendering a realistic image of the clothing is very important to potential purchasers, consumers, and so on. Fireworks have used surface-based models. So the pros are it's lightweight, it's fast, but it oftentimes appears more less realistic as it is surface-based. It does not have the natural depth, thus as with usual cloth. There is also volumetric micro-appearance models, which comes in the form of volumetric geometry and curve-based, fiber-based geometry. These are highly realistic because it contains the accurate geometry. As many works use CT scans and so on, and they might convert them into fiber-based to provide a more accurate geometry for the light to scatter on. But they are oftentimes really slow and very memory intensive. This is because for each ray, it scatters within the yarn and it hits up to hundreds, thousands of times before exiting the yarn per fiber bundle, which makes it really, really slow. So that is what we are trying to achieve, mitigate. Prior works try to aggregate this by trying to not use fiber-based, maybe on a higher level like ply-based or yarn-based, which are just the fiber bundles on one single fiber bundle. So these are observation-based, analytically based, and more likely than not more practical focused. So they might not give the best look, but they might be used for they might be used for their ease and convenience. So for the objectives of this paper, we're trying to have something that is lightweight and fast like surface-based models. But yet we still want the accuracy of the microgeometry models. So we want to preserve yarn apply at mid-level to far view. So what better way to learn how the light scatters within the fiber bundle, but to just use a neural network to learn the distribution. So prior works have been used to render neural materials where we just throw a neural network at them and try to figure out whether it works or not. Previous work might work because it's less complex, but for fiber bundle where there is high variance in values for sometimes certain components that go out of the yarn directly, or certain colors, certain scattering, some might scatter like hundreds of times before they exit, some might just hit once and just leave. So there is a very large variance in values, and as you can see, prior works might not be able to render them well accurately, especially if the high values blow out all the more softer colors. As you can see, it does not recreate the reference as well as ours would. So here is our methodology. On a high level sense, here are 5 steps. But before that, here are some preliminaries. So for the geometry, so you can see this is an illustration of how a fiber bundle would look like. The coordinate system you can just define. We use the Marshner 2003 coordinate system, and as we can just define it as XYZ, but yet we still want the fiber shading frame. For each certain fiber, we provide a twist factor as well. This shows how much rotation the fiber is twisted around the yarn. So we want to go back and forth between the yarn and the fiber shading frame. So how can we do that? just by using a simple rotation matrix. To calculate the simple rotation matrix, especially if this is along the z-axis, you can see that it uses a phi tilt. So that thing is taking into account the rotation of the fibers. So we can go back and forth between the yarn and the fiber shading. So if refer to the paper for more like details on how the twist factor and so on is defined. For each fiber bundle, to get all the data we need, we trace the rays. We shoot out millions and millions of rays to one single fiber material. We can use this to learn on how that specific material interacts with light. So we have many different components. First component being transmission. So for the transmission component, we just think of it as it does not bounce at all. It just exits the yarn immediately. Then we have a single bounce and it reflects out of the yarn. That is the reflection component. Anything else, it's a multi-scattering component. So that forms the three components of our implementation, the R, the T, and the N. So as you can see, those data can be collected into an RDM, a radiance distribution map. So here is a 2D slice of what is essentially a 4D radiance distribution map. You can use this as the training data, as well as to form any other certain evaluations on how this certain material interacts. Each bin is, as I said, it's by an omega I and omega O, so a 4D bin that has a radiance value. So now we'll first start talking about the reflection component. So the idea is, if it hits it once and it leaves the yarn, it is as if you are hitting a fiber. So I'll repeat that. So if it reflects out to the yarn, we can find the proportion of rays that actually do hit and means it does not transmit, and we can just use the fiber-based reflection instead. This forms the idea that for a single bounce, the highlights are created by the inherent specular properties of the fiber-based material. So now I'll be moving on to the transmission. For transmission, we are actually looking for how much of the proportion of rays are actually transmitting through the material without hitting the fiber bundle. So we have the data in the radiance distribution map tagged under T. So we can just look at T over all the rays for that given angle. So essentially, it's just a supervised, like a normal supervised task. For a given angle, omega I, we have an output of the probability or the proportion of the no bounce versus all the other rays shot out. So for the N component, multi-scattering component, we can look at the radiance distribution map directly because we already have a radiance value as well as the bins. So those can just be used directly for an omega I and omega O to form the radiance values of the output. So that inherently shows what would happen given an omega I and omega O, how much energy would be absorbed, given out, scattered for that given value. We've also improved on the pre-existing neural architectures to help converge faster, which is to change from ReLU, the activation energy, that improvement, into a PReLU, parametric ReLU. This helps it converge better as there's just more control over the neural network, such that you're able to get a more faster convergence. As you can see here. So an important sampling scheme would be best going with this pipeline. So to help reduce the variance of the image, we can define an important sampling scheme. So the key characteristics is for the PDF to sum up to 1. So the idea is we can use different PDFs from other works to help form our weighted combination of different PDFs. So for the transmission component, we can look at, if it's transmitted, the PT up there, we can just use the direct delta distribution. Why is it so? It's because you can think of, for a given angle, it shoots out directly. So there's a highly concentrated energy at the outgoing angle in a straight line. So that is the strong, highly concentrated energy as one will find in a direct delta distribution, because it is a direct delta distribution. So that is for the transmission component for the importance sampling. For the remaining part, the 1 minus PT, we can further divide it into the reflection component as well as the non-reflection, aka multi-scattering component. So we already have the analytical formula of the reflection component. You can just directly use it and convert it to the appropriate PDF. So that paired with the weights of the reflection component, we will be able to find the appropriate importance sampling scheme. And for the last part, the multi-scattering component, we can observe from the radiance distribution map that it looks something like that. So after observing it closely, we notice that it's actually it's a combination of the original fiber-based distribution, but on a much larger scale, and the uniform distribution. As observed in the radiance distribution map, this would how it would look like in 3D. So that reflects directly in our importance sampling scheme. So it's just a weighted combination of the fiber-based distribution on a bigger scale and the uniform distribution. So in total, our importance sampling scheme is just a weighted combination of all the PDFs above. As you can see, I hope you can see, the noise in the baseline uniform sampling and the importance sampling scheme before and after of trying to reduce the amount of variance. So here are the results using different components. So when we render each component individually, we get T, R, and M. So for T, what does T do? T is T, as you can see, there is like a glow band on top and the bottom. So those are more likely places where fibers are less dense and it will pass through the fiber material directly more, in which it gives that sort of glow. Whereas R, reflection component, that sharp highlight is due to only having a single bounce, and it's the specularity of the original fiber that gives out that strong highlight. And as well as M, which gives a more sort of diffuse color, which is based out of the multiple scatterings that has been aggregated into a more softer hue. Once those three are combined, we are able to get the top image, which is all of the components combined. Here are the results of different materials. There are more materials in the paper, but here are fleece and silk-like materials. So as you can see, ours are able to recreate the equal quality quite well, quite similarly, as well as for the silk as well. We are able to recreate the shadows, the highlights, and so on. The reference is actually based out of the fiber-based distribution. As you can see, there's like small little fiber highlights. So you can, it takes much more computation, much more, due to the way how the light scatters. And it's inherently slow, in which you can see in equal time, there's lots of noise, and how many is the equal time using F per hour rendering. And there's lots of noise, variance, and so on. Even though our material is neural-based, we're able to accurately represent ply-to-ply based interactions, meaning that it's still able to interact with other things and take that into account. So we can say that our material is quite robust and it's basically quite physically based as well. Yeah, so you can see there's single ply and multiply, where multiply of yarn forms one single yarn. Here are some comparisons with some state-of-the-art works, especially throughout 2023, the paper that was presented last year. There is quite a big difference between the state-of-the-art and the reference pictures, whereas ours are more closely matched. That is most likely because of the fiber model that they used in Duet of 2023. This, they used a more approximated model. They do not take into account the Fresnel weights and so on. So it provides a less realistic look and it would require more tweaking. They also contain a diffuse component that is supposed to be tweaked and adjusted to match the original reference image. Ours, on the other hand, is overfitted directly to the original material, in which means that there is no tweaking involved and we're able to adapt to any original fiber model. So here are some stats. It's all rendered on this laptop. It's a pretty old laptop. It has an i7. I bought it like 5 years ago. Not great. So let's just focus on the time. So the reference, as you can see, we improve it by quite a margin. So 10 times more. And as well as how much memory do we save. So memory is directly correlated to how much fibers we aggregate. So it might be 600 times, maybe 1,000 times, maybe 20 times, 30 times. It's really directly dependent on how much fibers we aggregate. So I'm just not going to bore you with that, and most of it is in the paper. But here are the more important results, which is the time. The time, we are able to improve by 10 to 15, 10 to 15, 20 amounts. Yeah, so these are the different materials, as well as improve upon state-of-the-art, where there is where they use an analytical-based solution. State-of-the-art also struggles with the highly specular materials, as it scatters more and provides more noise. So the dual scattering approach might not work as well, whereas ours are able to save up much more time by improving from around 3 to 20 times better. So here are the limitations and future works. Right now, as you can see, our radius distribution map only contains 4Ds, which is omega I, omega O. We do not provide subsurface scattering included. So future work could be on subsurface scattering, as well as further improvements in meta-learning. Meta-learning would be to use one single neural network instead of training a neural network, a set of neural networks per material. That would be one potential improvement, as well as there are recent works in neural-based sampling. So that could be a complementary approach to our neural-based work. So yeah. So in conclusion, we provided a neural aggregation approach of fiber bundle far faster than 3 to 20 times of state-of-the-art, as well as an important sampling scheme, which is complementary to our neural approach, as well as some minor improvements in the neural network architecture. Thank you for listening.